So thanks. I hope you're not too tired. So I will retell my thanks to Liz, who helped me prepare the talk, and some of the material in this talk is thanks to her. And I will start with some disclaimers. So it's a wide topic, like I said. It's potentially related to many astrophysical questions that can be of interest to you. And despite my best efforts, there will be strong biases towards star-forming dwarf galaxies, infrared tracers, cloudy models, and Bayesian statistics. That's one way for me to speak about what I know or what I think I know, and not to spend too much time on what I don't know. That said, I will present some plots and some codes that probably some of you have worked on for several months or several years even, and you probably are more experts than I am on that. And there are some people in the audience who could give a much better talk than me about this topic. So if I turn my head on the right side toward Brent, for instance, don't be surprised, and I hope you will help me answering some of your difficult questions and simple questions as well. It's not a talk about ISM models per se, adapted to a physical object or a physical process. We had very good talks by Benjamin and Pierre about H2 regions, PDRs, shocks and turbulence, and the physical processes at work. But this talk is going to be more about how to model kind of like everything at once, and what I like to call dirty models, because we try to do complicated things and try to make everything work together, knowing that it's not possible, but we try to do our best because we don't have a choice. And that's going to be a talk mostly about models that will attempt to match a variety of lines and processes, and that will relate mostly to large-scale environments and integrated observations of galaxies. And in that vein, it's not a talk about simulations, because I will focus on models that can be compared to observations and to specific objects, specific galaxies. And if you can do that, you can also compare to samples of galaxies, obviously. So the goal, I hope, the goal will be that it can provide you with some background on recent advances in the methods to make sense of integrated observations of galaxies, so that you can be aware of potential biases, but also existing strategies before choosing the right modeling approach, depending on the object you're trying to model. But it's also maybe one way for you to have a critical thinking of the results when you read a paper in the literature or when you interpret your own results, of course. And I will present some references, techniques, but it's far from exhaustive, obviously. So that's the outline. So I will first give some general considerations that will serve to motivate some questions that I will try to tackle in this talk. What are we trying to model? Why are nearby galaxies useful? What physical processes should we consider in the models? What constraints do we have? I will give an overview of some common diagnostics that are used for integrated observations of galaxies, but also spatially resolved, as we will see. Then I will go ahead on describing approaches to model full galaxies that will try to account for the complexity of the ISM and the complexity of the sources within galaxies. I will start by talking about 1D models and how we can make the best of 1D models. And that should take a bit less than 1 hour. And so we could take a break before going to the more complicated stuff of mixing issues, smearing issues, and maybe go beyond 1D models. And if I have time, I will finish with talking about statistics, because we're talking about many different models with many solutions, and the statistical framework is very important for that. So if I have time, I'll try to talk about that. So let's get started. What are we trying to model? We are trying to model galaxies. There are various kinds of galaxies, of course. You have your favorite type in here, probably. One thing to keep in mind is that the galaxies we're trying to observe, it's the result of an integrated history of star formation. It's the result of the integrated history of the active nuclear phases. Maybe there is an active nuclear phase right now. It's the result of interactions of gas exchanges with the circumgalactic medium and the intergalactic medium. What we see is really a snapshot of that history at a given time. And what we see is often a limited number of tracers, because we don't have the full wavelength coverage, because there is extinction, signal-to-noise ratio, etc. So it's a biased view, really, of the object that we have, and we're trying to use models to make sense of these tracers. And what is the object we're trying to model exactly? Well, we're trying to model galaxies, but it's not always easy to describe a galaxy, actually. It's not always easy to define a galaxy as a well-identified or circumscribed object. It depends on the wavelength regime you're looking at. And so often we will limit ourselves to the object as it appears in some tracers. And if you have unresolved observations, like high redshift observations, it's a hard guess. Of course, you don't know what the galaxy is made of. You can make assumptions, etc. And so these are just two examples. This is the M82 galactic outflow. We already saw that image from Benjamin's talk. And this is, sorry, the contrast is not very good here, but you have an extended UV and radio disk around M83. So, you could try to model that. And in some tracers, you will see only that, but the full galaxy is actually that. And so something that you might want to take into account if you model your galaxy. If you don't have spatially resolved observations, you don't know that. So it's something that you can try to either infer or take into account or ignore. It's a choice. Another thing to keep in mind is that the physical processes act on various spatial scales. So if you observe in different tracers, say H alpha, CO, H1, you will see something like that. So this is from the FANGS collaboration. It's an ALMA image. In orange, you see molecular clouds. The background gives the stellar emission with an HST image. And what I want to illustrate here is that it's not always easy to link a region with a specific excitation source. So you have some molecular clouds here, but you don't know actually what excites them necessarily. Even if you have the spatial information, it's not something easy to do. So let alone if you integrate all of that, it makes it even more complicated, obviously. So this is just to illustrate how complex the ISM can be. And often we have limited information. That's often the case for distant galaxies, but not only for distant galaxies. For instance, far infrared observations at redshift 0, the beam is so large that you are necessarily not resolving spatially your sources. High redshift galaxies, even with JWST, are hard to resolve. So with the photometry, you've seen probably some samples like this one. This is the Sears field. So you can see the structure of some very high redshift galaxies. But when we take spectra of these, the spectra are themselves spatially unresolved for the most part. And so what you will see is a redshift, I don't remember, it's redshift 9 galaxy or so. So you might see some structure here, but you have a single spectrum. It will be very difficult, even with JWST, to have spatial information. And so you have one spectrum for the full galaxy with some lines corresponding to different species, elements. And of course, the goal is try to make sense of it all. Okay, so some more considerations. Why are nearby galaxies useful? Well, let's start with external galaxies in general. There will be some more talks about that, so I'm going to be quick. But of course, it's interesting to study external galaxies because we care about galaxy evolution. We want to study the star formation rate, how it evolves with the redshift. We want to study the metallicity, the stellar mass, AGN fractions, stuff like that. So, for instance, some of you study the mass metallicity relationship, the mass metallicity star formation relationship. What's something I like to do is to look for metal poor or close to metal free gas in the local universe if possible, but also in the reionization epoch. And so there will be presentations about some of these things. If you care about multi-line modeling, it's also maybe because you care about the ISM, I guess. And so it's interesting to think about what is the role of the ISM in the star formation process? And for instance, what is the role of the molecular hydrogen in the star formation process, especially at low metallicity? That's an open question. And we want to have like tracers of H2, fine tracers of H2. And in my mind, it's interesting to think of the ISM as an astrophysical object by itself, like stars, like compact objects, an astrophysical object that gets formed, that evolves in like any astrophysical objects. Now, if we turn to nearby galaxies especially, they are very interesting because it's a great opportunity to understand the extragalactic ISM in a very different environment than in the Milky Way. And they can be useful because they will help us design relevant models that can be used for more distant galaxies. And indeed, some nearby galaxies are nearby enough that we can resolve them. And we saw some example in the previous slides, and that can help us disentangle the various physical components in these objects. And so one open question here, one motivating question for this talk is, should we model the sum of individual regions within a galaxy, or should we model the entire galaxy in its entirety? And do the results change if you do one or the other? And basically, more generally, do the results change depending on the spatial scale you consider for the models? I'm not sure I will provide the answer to that, but that's an interesting question, and I will do my best to try to give some elements of answers. Another reason why we study nearby galaxies is because we have a bunch of tracers. Some are nearby enough indeed to be bright enough that we can detect many, many tracers arising from different phases. This is just an example. You probably don't see the axis, but this is the mid-infrared spectrum of ARP220, a nearby galaxy, in the mid-infrared with Spitzer, in the far-infrared with Herschel, so between 200 and 500 microns here. This is just to illustrate the fact that you have a bunch of lines, PHs, of course you have the dust emission, but you have really a lot of lines coming from different phases. And these observed tracers, they are signatures, and they are signatures that reflect the complexity of the galaxy. And if you take it inversely, the complexity of the model, the complexity of the physical representation of the galaxy should reflect these tracers. And I will go even further than that. It should also hopefully reflect those that we don't observe yet, for which we will make predictions and test later on. And so one motivating question here is, what kind of useful information can we get from a limited amount of tracers, 2-3 lines maybe? Do the results change depending on what tracers we use, the choice of tracers we use? And should we consider very simple models because we have very few tracers, even though we think that the models are not realistic? So that's an open question. And again, I will try to give some elements to answer that. Another reason why we study nearby galaxies is because we have interesting neighbors. So I care about low metallicity galaxies. So this is something I work on specifically. Some nearby galaxies probe a very different environment compared to the Milky Way. I talked about that. There can be AGNs, the presence of superstellar clusters, but also low metallicity environment. And this is just a plot showing the metallicity versus distance. It's an arbitrary sample, don't read too much into it. But this is just to illustrate the fact that you don't need to go very far with the Magellanic Clouds to reach moderately metal-poor sources. And if you go to a few megaparsecs, actually some galaxies are missing in there, but you can go to a few megaparsec and reach metallicities 1/30th, 1/40th solar metallicity, which is really low, especially when you know that below 1/10 solar metallicity, a lot of things start to break down. Considering the low metallicity, you also need specific prescriptions. We have to be careful with that. So use proper abundance patterns versus metallicity, use the proper dust to gas mass ratio versus metallicity, etc. So I will try to talk about that also. Okay, so now what physical processes do we consider when we want to model galaxies? There are plenty of physical processes at work potentially. And I like to think of the model parameters that we would like to implement, to consider in the models, in 3 different categories. First, the parameters that describe the matter. So that's the gas, the dust, the composition of the gas, the dust size distribution, the dust properties in general, and also the spatial distribution of the matter, of the gas and the dust. Is it mixed or not? And there are various questions that are related to that. Then the parameters that control the excitation of the matter. So it's related to all the radiative and mechanical energy, mechanical processes. And I will talk about that in the next box here. And then there are parameters that link both the matter and the excitation sources, in particular the ionization parameter U, which is the flux of the ionizing photons divided by the density and the light speed. And you can rewrite it as the number of ionizing photons divided by 4 pi, the distance squared to the illuminated edge of the nebula, and NC as well. Now, there are a wide variety of radiative and mechanical feedback processes. We've heard a lot about some processes already. There's the ionization and heating of the various ISM phases. So the ionized phase in the H2 region, or the diffuse ionized gas, the neutral atomic gas, the neutral molecular gas. Young stars will emit in UVs, and also some amount in the X-rays. You will have Wolf-Rayet stars, AGNs, X-ray binaries that shouldn't be neglected. Cosmic rays, turbulence and shocks, magnetic field, molecule formation and destruction. So it's just some examples that I try to put in this plot. It's a complicated plot, but I'll try to guide you through it. So it's a 1D model basically, or 1D onion layer representation, whatever you want to call it. You have the H2 region in here, the neutral atomic gas, the neutral molecular gas, and you have a layer here which is the CO dark layer. We talked about that this morning, but this is a region where the gas is molecular, but CO is not emitting because it's photodissociated, while H2 is self-shielded. You have some OB stars. The radiation above 13.6 eV will be used to ionize the hydrogen and helium. The photoelectric effect is negligible. And so that's the main heating mechanism, the photoionization. And the main coulants, it will be the collisionally excited lines like O3, 5007 angstroms. There's also the free emission, and at extremely low metallicity, the recombination line Lyman alpha may dominate actually as a coulant. The photons below 13.6 EVs can go through the H2 region, and they will reach the H1 region, so the neutral atomic phase. Then they will participate in the photoelectric effect heating on grains or pH-like particles. The main coulants will be C2O1 in the far infrared. Not to be neglected is also silicon 2 and iron 2, especially at low metallicities, because less of silicon and iron will be locked into the dust and more will be into the gas phase, so they will participate to the cooling. And another thing to consider is that you might have compact objects that emit copious amounts of X-rays. And so depending on the energy of these X-rays, they will deposit their energy more or less deep in this gas as a function of the depth here. So for instance, soft X-rays might deposit their energy mostly in the neutral atomic gas, which will partially ionize the neutral gas. So it's still called neutral gas, but it's partially ionized, and it's very important because the electron fraction is much higher than what you would get with the photoelectric effect heating. So it might change the chemistry, it will change the temperature of the gas and change the diagnostic power of these lines as well. The harder X-rays might just go through for most of them and deposit mostly their energy in the denser phases where the gas is mostly molecular. And here there are plenty of mechanisms that I don't understand, so I won't talk too much about that with some coulants, specific coulants here. But I will mostly focus on these two phases here. So knowing all of that, we tend to make some approximations because it's impossible to do everything right, to include the turbulence, the magnetic field, the time evolution, the chemical network. It's very complicated. That's why often people will tend to rely on specific galactic regions like H2 regions only, or molecular clouds, or maybe focusing on galaxies dominated by certain processes like AGN-dominated galaxies or H2 galaxies, which are dominated by an H2 region-like spectrum, for instance. Another thing that we tend to approximate is also, or to simplify, it's the typical timescales problems with the compact objects, transient phenomena, because there is a disconnection between the radiative phases of the AGNs or X-ray binaries, which have state transitions, and the observed ISM tracers. And so these compact objects, first of all, they have, for a lot of them, non-isotropic emission. So not all the gas sees the light from the compact objects. Then there is the time for the light to propagate and to reach the gas that will eventually cool. But there is the heating and cooling time scale that you have to account for also. And that's why, for simplicity, we will assume that the inferred properties of the transient objects are the inferred properties seen by the matter when it cools down, and it's not the properties of the transient object as you see it, the compact object as you see it in the X-rays or whatever. And that's something important, I think, to know. And this is just an illustration showing the AGN feedback luminosity in some simulations with a varying supermassive black hole accretion rate. So whatever the scale here, I just want to show that this changes with time. And so the line emission that you see in some galaxies might be related to a phase that is here or here, not necessarily at the moment zero. And that's something that also should be kept in mind when we infer the properties and when we try to infer the luminosity, for instance, of these compact objects. There's a time scale issue and we try to simplify it. So what constraints do we get and can we use? We heard about dust. Dust is, Natalie presented to us this morning how essential it is, and it is an essential part of the models. The dusticity itself holds much information, of course, about the local physical conditions, the dust properties, but also the gas mass through the dust mass, through the dust to gas mass ratio. So you get a lot of information from it. One difficulty is, though, is that it's difficult to disentangle the various ISM phases, for instance, those associated or not with star formation, especially if you have integrated galaxy spectra. This is just to show the dust to gas mass ratio as a function of metallicity here, an important prescription to use in the models of external galaxies. So in this talk, I will mostly talk about line spectroscopy. Gas tracers are very useful because they may constrain different phases, and what I will call phases can mean different things. It can mean the hydrogen phases. So I showed already the phases of ionized hydrogen, neutral atomic, neutral molecular. It can be also the ionization of some metals that can be traced by some ratios like O3 over O2 in the optical. It can be also different phases in density. And we have some tracers like the S2 line ratio in the optical, the S3 line ratio in the infrared that can help you derive the density, etc. The gas tracers can also help you identify the specific excitation mechanisms. It can be X-rays, shocks, especially high ionization lines like neon 5 and others can be very useful for that. Neon 5 is observable in the optical and the infrared, but I will come back to some other tracers that can be used for that. And the complicated part is that a lot of these tracers, especially for different excitation mechanisms, they are sometimes seen in a single spectrum. So this is just an example of it's the center of a galaxy, and you see different lines, including molecular hydrogen. So here you have different phases. And of course, we would like to try to make sense of all these phases at once, which makes it complicated. In this talk, I will mostly talk about emission line spectroscopy and not absorption line spectroscopy, even though absorption spectroscopy is extremely useful. You can do many things with absorption lines, derive the chemical composition, you can study deuterium, depletion patterns, cooling rates, molecular gas fraction, even the CO dark gas H2. And I encourage you to read the papers of Balashov et al., who does the similar kind of studies that we do in nearby galaxies in emission, but using absorption lines. And so it's very interesting stuff. One thing, though, in the absorption line spectroscopy is that we're limited to a single line of sight, and there can be some problems with it. So this is just a plot showing the different configurations that can happen in absorption line spectroscopy. So we are going to point at a far UV bright source, typically a QSO. So if it's high redshift, it will be shifted in the optical, but the principle is the same. So you have a far UV bright source that will give you a continuum, and then you have absorption lines in the intervening medium. It can be the Lyman alpha forest, and you will have also Milky Way components along the line of sight. What you can do is point at the QSO, and then the line of sight will intersect clouds within a nearby galaxy or different redshifts. It's one way to probe the circumgalactic medium or high velocity clouds in external galaxies. You can try to point at a far UV bright star. A single star in an external galaxy is difficult. You need spatial resolution for that. In the Magellanic Clouds, it's possible toward the Magellanic Clouds, but with the current facilities and old facilities, it was difficult to do that beyond the Magellanic Clouds. And finally, you can try to point at an H2 region, so it's stellar cluster that is not spatially resolved, and that gives you kind of one single line of sight, except it's not one single line of sight, it's an average line of sight. It's difficult to interpret, but that's one way to probe the absorption in a nearby galaxy. And of course, you still have the Milky Way clouds along the line of sight. So it's interesting. One thing to understand also is that the comparison between the results obtained in absorption and emission are not straightforward, especially because of this line of sight versus integrated emission. It's very complicated. And I gave some references if you want to have a look at how complicated it can be. But it has some future for UV spectroscopy. The Habitable Worlds Observatory is becoming concrete, and it's one of the recommendation of the NASA Decadal Survey. It will provide far UV to near infrared spectroscopy, including should be at very high spectral resolution and high spatial resolution as well. Unfortunately, it's in the distant future, so there will be at least 5 US presidents in between, but hopefully it will still happen. It's a big project, but it will really put back to the table the far UV spectroscopy for the redshift 0 universe. Another consideration, it's worth noting, it's obvious, but I still want to mention it. What we model is what we can see. And so the diagnostics that we can infer are the diagnostics that we infer for the regions that are emitting. Of course, we don't constrain what doesn't emit because we don't see it. And so as a result, it means the results can be biased by selection effects of the emitting components. There can be also some bias because of extinction. Some regions are extinguished and we don't see them, so they don't contribute to the emissions. So what we constrain is really what emits. And as much as possible, such effects need to be accounted for a priori or within the models if possible. It can be inferred eventually. What kind of processes do we include? The modeling gradients, the physical processes. I already presented some of them, like AGNs, etc., X-ray binaries. What I just want to say here is that you can limit yourself based on the assumptions of what kind of galaxies you're trying to measure, and you're not expecting some physical processes, so you're just ignoring them. But it's very interesting always to explore different processes, even unexpected, to see what kind of influence they could have on your results and have a broader view. Another thing that is worth noting is that the emission, so for the regions that do emit, they may arise from different regions. And as an illustration, the S2 line ratio in the optical that I mentioned, which is a density diagnostic, is indicative of the density only around the ionization front. So this is a 1D cut of a nebula. So you have the illuminated edge here, you have the ionization front here. So basically that would correspond to the spherical shell here. So you have the ionization fraction here. So this is O3, N3, and you see N2 and S2 are very close to the ionization front. So if you do measure the density of O3, it will be the density close to the star. If you do measure the density with S2, it's the density at the ionization front. And something very important to notice, it's not representative of the density of the entire galaxy. I will come back to that a bit later. All right, so now I will talk about some common diagnostics. We have many signatures potentially available. You might be interested in the primary modeling parameters themselves. For instance, if you have a grid of models with density, metallicity, the density might be of interest to you. It might be your main goal. Metallicity could be your main goal, but you might be also interested in other physical parameters that can be deduced from the models if the right processes have been accounted for. For instance, if you wanted to include AGNs, you should. And so some parameters are relatively trivial to deduce from the primary parameters. It can be star formation rate, the mass of ionized gas, the AGN fraction, it's relatively trivial. Some are not trivial at all, like the escape fraction of ionizing photons, the mass of molecular hydrogen, and I'll come back to how difficult it can be if we assume a very simple geometry. So we have many potential diagnostics. Historically, long slit spectroscopy of galaxy or integrated spectroscopy of galaxies has been used to probe so-called average physical conditions or average chemical composition or the dominant excitation sources of galaxies. I will show some plots illustrating all of that, but I will go very quickly here. So diagnostics about the electron density, so the gas density if it's fully ionized, the ionization parameter from some line ratios, diagnostics about the chemical composition, so the abundances, metallicity, depletion patterns, diagnostics about the star formation rate using some lines or some photometric bands, diagnostics about the excitation sources, the so-called BPT diagrams from Baldwin, Phillips, Tarlevich, that can help you distinguish the excitation mechanisms, for instance, AGN, can be versus mass or versus redshift, coronal lines to indicate AGN activity, UV diagnostics, so a lot of diagnostics. Let me go through some of them to illustrate. These are some density diagnostics. So all of these are line ratios in the UV, optical, and infrared. This is from the review of Lisa Cooley et al. What you see is that there is a low density regime where the ratio is about constant. There is a high density regime where the ratio is about constant. And then there is a transition regime. And this is where the line ratio becomes sensitive to the density. What's interesting to notice is that where it becomes sensitive to the density happens at different densities. So you can use various line ratios to probe the density. Now, the density, like I said, it depends on what part of the nebula you're trying to model. So you might get different answers. You might not get exactly the same density from all these line ratios because they don't emit in the same part of the nebula. But it's very good to have as many density diagnostics as possible, especially if you want to infer the density structure of your nebula or your galaxy. So these are some examples of BBT diagrams. You have seen a lot of them. So 3 over H beta and 2 over H alpha here. You can have it also with O1. And basically, this is often used to distinguish between star formation dominated or AGN dominated excitation. I'll go quickly through it, and because I think I'm going to show some more afterwards. Then you have some line ratios that are very useful to probe the AGN fraction in galaxies. This was a work done to prepare for JWST and try to see what line ratios are the most promising in order to quantify the AGN fraction in galaxies. And this is for given black hole mass and for various geometries. And I'll explain a bit what coincident or non-coincident means. The point is that, for instance, oxygen 4 over Pfund alpha in available with JWST is a promising tracer for the or quantitative way to measure the AGN fraction and potentially the black hole mass as well if you have several line ratios. You also have coronal lines. So these are high ionization, high excitation lines. I mentioned neon 5. Where is it here? It's in the optical. You have some in the JWST domain, but in the optical, you have other lines like argon 10, iron 14. And these lines are very interesting because they can be used as more unambiguous tracers of AGN activity. Even neon 5 is complicated. It can come from radiative shocks. And so the point of these lines is really to decide, okay, there is AGN activity. And this is very useful, especially because sometimes the optical diagnostics, like the BPT diagram I showed you, they are ambiguous and they can suggest star formation when in fact there is clear AGN activity, judging from these coronal lines. And I encourage you to look at this paper if you want to know more. And I'll continue on the illustrations of all the tracers we may have to interpret integrated observations of galaxies. Now talking about UV diagnostics. So these are UV lines between, I think it's like 1300 and 1900 angstroms. And so the points are the same, but the grids are different. You have shock models here, you have AGN models here, and you have star formation models with different assumptions. The point is that these grids lie on different in different parts of the plot, and using different line ratios may help you to distinguish between the excitation mechanisms. The point of the UV diagnostics is very interesting, is that it will be available again in the future with Hub World, like I said, but the shift in the JWST range at high redshift. And I think, yeah, it's in a couple of slides. So I will show you that we will access these UV diagnostics again, and it will be very interesting to have the models get ready for them. Spectroscopic diagnostics have a bright future. As you know, there are several missions or ground or space-based missions that provide wide field or all scale optical or near-infrared spectroscopic surveys. There's SDSS-5, started in 2020, the Euclid that was just launched, Rubin, Roman, then Sphere X, and that will provide millions of spectra that are, some of them are spatially resolved, a lot of them are going to be integrated, a lot of them are going to be for dwarf galaxies because most galaxies are dwarf galaxies, and there will be low surface brightness galaxies also, and this for a wide redshift range. So we will have the need for such diagnostics in the future. Just a quick word on infrared spectroscopy. JWST is observing much fainter infrared lines compared to Spitzer, which will mean new diagnostics, and we need to understand these new diagnostics and with the help of models. Like I said, at redshift 0, the mid-infrared spectra, the far-infrared spectra are mostly spatially not resolved because of the large beam. And that will remain the same even for a potential future infrared NASA probe class mission like PRIMA that is proposed. And that will remain so until we have some kind of infrared space interferometry. That's for the mid and far infrared. High redshift spectroscopy, well, JWST is providing optical diagnostics at very high redshift, but most of them are spatially unresolved. So we have the need to understand integrated spectra of galaxies, at least until ELT that will start resolving galaxies at very, very high redshift. There are exciting JWST and ALMA synergies, and ALMA at high redshift, there are a lot of papers on the topic with several lines observed at high redshift that already probe the multi-phase ISM nature in high redshift galaxies with lines like C2 and O3. So 2 lines and 2 phases already. Like I said, the UV diagnostics shift to near spec of JWST when the optical diagnostics shift to MIRI of JWST, which makes UV diagnostics very interesting. And this is, again, another complicated plot, but I think it's interesting to show. This is the redshift. This is the visible domain, the JWST domain with near spec here, MIRI here. This is ALMA and NOEMA and SKA, and you have various lines. And now you can see the UV lines here. So at redshift 0, they are in the UV, so it's on the left. But as you increase the redshift, they shift to the visible domain. And then they shift to the near spec range of JWST at redshift more than 2 for carbon 3. You have the Lyman continuum at redshift 6 here. And then the optical lines are here. And so these, so at redshift of a few, they start already being in the near spec range, and then they shift to the MIRI range. And then you have the infrared tracers that are there, that they shift to, well, something that doesn't exist here, which is why we need far infrared mission like PRIMA, hopefully, but there is a gap here and that we need to fill. Then you have the far infrared lines that are here that shift to ALMA and NOEMA at high redshift. And finally, you have the CO ladder here that shifts to SK at very high redshift. Now, what I want to show with this plot is that there are 2 sweet spots. There is a sweet spot below redshift 2, between 0 and 2, where the UV diagnostics shift from the UV to the optical range, where the optical tracers shift to the near spec range. Sorry, it's right here. Where the near infrared tracers shift to MIRI, it's right here, and where the CO ladder is available with ALMA, right here. There's another sweet spot at redshift 7, where the UV diagnostics shift to near spec, the far infrared tracers shift to ALMA, and the CO ladder shifts to SK. And the last thing, I mentioned it, but the far infrared diagnostics will remain unavailable at redshift 0 until a potential mission like PRIMA. The mid-infrared diagnostics will remain unavailable at redshift 210 also until potentially PRIMA, so it's 2 good reasons to have a far infrared spectroscopic mission in the future. I talked about integrated observations of galaxies, but of course you can have spatially resolved observations of some galaxies for the most nearby ones. So there are some instruments and surveys, you know, probably all of them. There are some surveys in the local universe, like MANGA, Fong's Muse recently, in the high redshift universe, like KMO 3D, since this is not an exhaustive list. And with these, you can do integral field spectroscopy observations, which means that each pixel in this map here, it's a spectrum. So you can extract the line emission map for various lines. So for each pixel here, you can have one position in the BPT diagram and decide on the excitation source, the excitation mechanism spatially. And so you can have the different excitation sources mapped really, spatially. These are just some examples. And this has also a bright future because there will be things like Blue Muse, SDSS5 with the local volume mapper that is starting, and in the future, instruments on ELT. So integral field spectroscopy observations is one thing, but you can also do narrowband imaging. It's worth mentioning if you have the right combination of redshifts and lines that you want, then you can do that. So this is an example with HST, where through narrowband imaging, you can isolate the O3 emission, H alpha, S2, H beta, and you can do a specially resolved BPT diagram just like that without high resolution spectroscopy or moderate resolution spectroscopy. So now that we have all of that, how do we make the best of the existing observations and the future observations? I presented a bunch of empirical diagnostics, and we really need to understand these diagnostics better. We need to understand the potential biases, the potential selection effects, the meaning of average quantities. What do we call average quantities exactly? And we need to design also new empirical diagnostics for future observatories, be it JWST, PRIMA, or others. So that's what we need to do. And we also would like to access some complicated physical parameters like masses, tracers of the molecular mass, the molecular hydrogen mass, so C2, O1 in the far infrared, OH, HG are potential tracers of the H2, that can be also the CO dark gas. So it's important to access this, but it's very complicated to get through models. Anything related to the ISM structure, the Clump distribution, the escape fraction of ionizing photons, these are complicated parameters. And for this, we would like full-on models, and empirical diagnostics are unfortunately not enough. In general, multi-phase observations will require full-on models. And ideally, of course, we would like to do that at any redshift. Okay, so now I'm here. So how do we model full galaxies, and how do we account for the complexity of the ISM and the sources? So I will start simple and get more and more complicated. So first, using simple 1D models. And first of all, there are some favorable cases for which you can use 1D models. It's well adapted, so it's working relatively well. These will include single H2 regions, single molecular clouds also, but that might also relate to H2 galaxies, which are dominated by a single or a few giant H2 regions, or AGN-dominated galaxies. These are all favorable cases for which you can assume a single ionizing source, or that all sources are co-spatial. And this is an example of the 1Zwicky-18 galaxies, my favorite galaxy. You have the stars here, you have the H-alpha shells around, so everything looks good. You have the shells around the cluster. It's like a modeler's dream. And so you can assume a spherical geometry. It works pretty well. So it works so well, actually, that you can even envision a full 3D model for this kind of cases, like Cloudy 3D or M-Cube. And in the next two slides, I'm going to explain what these are. I mean, or very, very briefly, but these are full 3D photoionization models. So M-Cube is very interesting. You cannot see here, maybe you can see it in your screen if you have the PDF, but you can model things like blister H2 regions, bipolar H2 regions, even fractal H2 regions. It's very, very powerful. It's the same principle for Cloudy 3D, which became PyCloudy. There is now the visualization tool PyCross that is linked to it. Just very quickly, the principle of Cloudy 3D is that you will define some modeling gradients and some density structure. So along a few directions. And then what Cloudy 3D is going to do is that it's going to interpolate these density profiles, basically, in order to sample well some kind of geometry that you define yourself. So you define the angular laws of the density profiles. And then what will happen is that all these cloudy models are going to be run, and it's going to be run to compute the emissivities of all the lines. The emissivities are going to be introduced in some cube. So it's going to make an emissivity cube. And then that emissivity cube, you can project it the way you want, and you can reproduce some observations. So it's very well adapted to specific objects for which you know very well the geometry, like planetary nebulae, single H2 regions, these kind of things. But it's very powerful. More generally, with the 1D models, so most of the cases, you cannot do what I just showed you. So you will refer maybe just to single 1D models. You have various codes that you can use. You have line and dust radiative transfer codes, and you have photoionization, photodissociation codes. So first, for the line and dust radiative transfer codes, you have codes like RADEX, RADMC that you probably know. They can use local thermodynamical equilibrium or non-LTE. And there are some approximations like escape probability or large velocity gradient, which is itself an escape probability formalism. There is no photoionization, there is no chemistry, but you can do very interesting things with it. It can be potentially spherically symmetric. And what it can give you is things like the column density, the density, what's the column density of some species, the local density, the temperature, and this through the generation of synthetic spectra and grids that you can compare to your observation. If you want to do something more fancy with more physical processes and you want to have photoionization, you can use 1D photoionization codes or photochemistry steady state models like cloudy mappings, Meudon PDR. One thing to bear in mind, though, is that these models can be very long to run, and that's something to take into account if you would like to do, for instance, MCMC methods, where for each draw you would like to run one model. This is not possible to do that, so you have to find other solutions. And in this presentation, I will mostly talk about this kind of models. So with this kind of models, what you can do is, well, you can do various things, but it's very useful to link the observable to some average physical conditions modeled by the 1D model. So like I said, you might be interested by the parameters of the model by themselves, the density, the ionization parameter, maybe it's your goal, but you can also be interested in other physical parameters. And it's worth noting that some codes actually provide plenty of output quantities and predictions once the code has run, and predictions that you can examine, things like the formation pathways of H2, for instance, in the gas phase, on dust, etc., or X-ray photoionization. I mean, the list goes on and on and on. So, but these are output quantities that we can really extract from all these models. Like all single 1D models, the assumption is going to be that you have one ionizing source. So if you have several ionizing sources, the assumption is that all the ionizing sources are co-spatial. So if you have several stellar clusters, the assumption is that all the stellar clusters are co-spatial. If you have an AGN, the AGN is co-spatial with the stellar cluster, and so on. And I will show that you can deviate from this hypothesis, but that's usually the common assumption. So if you use photoionization or photodissociation codes, you will have to ingest some prescriptions in there because it has default values, and you don't want to use necessarily the default values because your galaxy is a certain kind of environment, etc. I already mentioned the abundance patterns. They do vary with metallicity. That needs to be accounted for. The dust to gas mass ratio does vary with metallicity. The dust properties, that's complicated. I'll mention it right at the end here. The equation of state, so the density, the pressure profile is something you have to account, you have to assume. So some people will use a constant pressure, especially to reach into the molecular gas, and that's motivated by observations and models of the Orion Nebulae, but also it's valid for diffuse and translucent clouds. You have this paper here showing that historical paper. Problem with constant pressure models is that you will reach high densities very quickly, and that might be good for a single PDR, yes, or a single H2 region plus PDR model, but that might not be good if you're trying to model a full galaxy with one single 1D model, because that high density that you will reach is not representative of the average density you expect for the entire galaxy. So there are various things you can do to kind of mitigate this problem. You can have a density scaling with the column density of hydrogen. You can also include a magnetic field pressure term, which is going to add a pressure term, which is going to reduce the density you need to get to have constant pressure, basically. You also have things like pseudo constant pressure models where you will have two pressures, one for the H2 region, one for the PDR. So there are various ways that you can try to for which you can try to have different equations of states that will be more practical for integrated observations of galaxies. Shocks, it's complicated. In codes like Cloudy, this is the one I know, that's why I mentioned it, but you can use a mechanical heating term. So it's a flat heating rate that you can actually compute analytically, for instance, with a supernovae rate in your galaxy. And you can make it vary with the depth or not. It's an assumption, but it's one way to include shocks. It's not the best way. Cosmic rays, it's also complicated to have the proper prescription. What we know is that nearby starburst, nearby Euler's, all suggest Milky Way-like range values, and this range is big, between 10 to the minus 16 and 10 to the minus 13, depending whether you're looking at the disk or the nuclei of the galaxies, depending if you're looking at regions with intense star formation or not. So it varies quite a lot. And depending on the galaxy you're trying to model or the different components in your galaxy, this is a range that you could explore. Another prescription is that of the stellar atmospheres. So you have photoionization, you have ionizing sources. Some of them will be stars. You have stellar population synthesis models, like BPAS, for instance. These models keep changing all the time, and your results will change depending on which stellar model you use, stellar population model you use. And it's always good practice, a good habit to test how the results change with the new version each time. They keep changing, improving these models, and it really has an important effect on the output quantities that you might be interested in. And the last note I wanted to say is that at extremely low metallicities, a lot of things break down, the dust properties change. And so we have little knowledge on the dust opacity curves, little knowledge on these cosmic ray prescriptions at low metallicity, little knowledge even on the stellar atmospheres. So we have to be very careful when we interpret the results from the models at extremely low metallicity, and in a way assume some kind of systematic uncertainty, which is very difficult to quantify. But it is there for sure, and it is related to the model assumptions here that might not be completely correct. Right, I just wanted to show some codes. I haven't used them myself. Maybe you know them already. But if you have 1D models, you have various ways to compare to your observations. It can include large samples even. So this one is a supervised machine learning technique. You have a spherical geometry, it's 1D model. You have synthetic spectra and a library of different spectra with known physical parameters. And you can train a neural network to work on them, and you can make predictions for an arbitrary suite of lines. It works very well. It's called GAME. And in my mind, the interest of such method is that they are extremely fast. And you can work on large sample of galaxies, or you can work even on large number of pixels within IFS observations. So there is an application in this paper here. And so it's much more performant than Bayesian techniques in that regard. Yeah, so it's just more performance and it's just faster. Then you have some probabilistic methods and SED fitting tools that you know probably. There's Beagle, there's Seagal, which is the next slide. In Beagle, they used the Gutkin et al. Models. And these models, they combine some stellar population synthesis models and photoionization codes. And the goal is to describe an ensemble of H2 regions and the diffuse ionized gas. And the assumption is that there is some kind of effective H2 region, and it's a very common assumption, actually. So basically, all the H2 regions and all the diffuse ionized gas is going to be ionized by a single stellar generation. And what you will derive is a set of effective parameters. So it's a strong but classic assumption. And it's just an assumption right now, but actually they are investigating the effect of a collective emission of H2 regions. It's being investigated right now. And toward the end of the slide, I'm going to mention also how we can do that with combination of 1D models. It's a little bit the same principle here, but since it's not published yet, I will show you some work in progress that kind of does the same thing. The geometry in Beagle is basically accounted for by using a dust attenuation law or different laws, different prescription for the stellar emission and the nebular emission. So things like inclination, disk versus bulge can be accounted for. It's a very powerful algorithm that can include instrumental effects. And if I have time at the end, I will talk about the statistical framework to make sense of all these models to try to find the best parameters, PDFs of parameters. And in this case, they use a nested sampling technique to account for multimodal posterior distributions, because ISM models are in most cases, they will have several solutions, especially if you combine models. So you want to have a sampling technique that accounts for potential different solutions. And there is Seagal. Seagal relies on, actually I've never used Seagal, I have to say, so correct me if I'm wrong. It relies on energy balance principle. The idea being everything that is absorbed by dust in the UV and optical will re-emit in the infrared, and it's keeping the energy balance in line. There are several geometry templates for the dust attenuation. Recently, there was a detailed treatment of the X-ray sources in this paper here. The nebula emission was, if I'm not mistaken, treated before, but mostly as a way to decontaminate the broadband photometry to try to have the most diagnostic power for the photometry. But the line predictions for the H2 region and PDR is under development right now. So there are exciting developments from all sides, machine learning, Beagle, Seagull, etc. It's very exciting times with a bunch of methodological improvements. These are all 1D models, and so there are common limitations for all of these. Like all static 1D models, 1, 2, 3D models, they just can't capture the complex and dynamic structure of the ISM, along with the relevant time-varying star formation and feedback. They are steady-state models. Like I said, 1D models assume co-spatial sources and some kind of effective galactic-wide parameters. Common assumption and OK assumption, I think, in most cases. Like all parameterized models, so you have a grid with some parameters that change, you define that when you make your grid. Like all parameterized models, there is a wide range of theoretically allowed parameters, but these might not be realistic. You just don't know. You don't give any a priori information on what's supposed to be realistic or not. So you explore a huge parameter range, and you might not need to, and actually you might find some solutions that are completely unrealistic that simulations tell you it cannot even exist. So it's really something to keep in mind. And like all single 1D models, of course, the distribution or geometry of gas is really difficult to implement, especially if you have complicated objects like evolving H2 regions, PDRs, molecular clouds. And this is the point of the next slide, where I show, oh, I forgot to put the reference, I think, sorry for this person. I can find it again. Oh, no, it's here, sorry. Yeah. This is a star forming region that is going to evolve. You have an H2 region that is going to form, and then the supernovae and the stellar winds that will form are going to create some channels through which escaping photons and gas can escape. And so if you have this kind of configuration, of course, even with a spherical 1D geometry, you cannot capture the complexity of such a region because you have some holes in there. And it's interesting to see that observationally, we do see things like that. It looks surprisingly similar, although the scales are completely different. It's not an H2 region, it's a galaxy at a few megaparsecs, I don't remember. This is a Muse observation where you see in green here some channels of O3 emitting gas. And this is the sign that you have escaping photons escaping in several directions. And that corresponds well to this kind of sketch here. But anyway, this is just to show that such complex objects are difficult to model with single 1D models, except if you have 1D model like that, 1D model like that. And basically that is the start of combining 1D models, which will be something that I will mention in a little bit. And so if you have single 1D models, there are several tweaks you can try to improve the approach to make it more realistic in a way. You can assume different kind of spherical geometries. You can account for holes, like I just showed. You can account for matter bounded or density bounded models. I will explain what that means. Maybe Benjamin, did you? No, okay, so I will explain what that means. And then you can also account for time evolution. Let me start with different geometries. This is oxygen 3 over oxygen 2 in the optical, argon 4 over argon 3 in the optical. You have some points here. I don't remember the sample, it doesn't really matter. But the grid here, the photoionization grid, assumes two different things, either a field sphere or a thin shell. And you see that the grids actually shift a little bit. So these are two different assumptions. A priori, you don't really have any reason to choose one over the other. You might want to try both and see what matches the best, maybe not 2 line ratios, but several line ratios, and see what works. So this is an interesting test to do, but playing with the geometry is not going to be enough in some extreme cases, or maybe I shouldn't say extreme cases, but some complicated line ratios that will involve lines that emit at different depth within the nebula. That includes O1 over O3 in Lyman continuum leaking galaxies, so leakers, the one that will have ionizing photons escaping, or C2 over O3 in high redshift galaxies. And I will explain why in the next slide. So these are some so basically you have, let's see, I'm going to start with here. So you have a radiation bounded or ionization bounded nebula with holes. And radiation bounded means that basically you will run out of ionizing photons before you run out of matter. So you're going to ionize completely your H2 region here, and then you're going to reach the neutral gas because you don't have any more ionizing photons. But you can have matter-bounded regions or density-bounded regions where you run out of matters before ionizing photons, and so you will have ionizing photons left that will continue their path here, and so this is not fully ionized. The point of this is that it kind of complicates everything, and it gives a different vision of the diagnostics that we like to use in nearby galaxies or for the high redshift. Because, for instance, matter-bounded nebulae, what they will do is that they will provide the regular amount of O3 emission because it's, like I showed before, it's emitted close to the star. So you will have, even if I cut here, you will have pretty much all the expected O3 emission you get. But you will miss some H recombination line emission from here. And so that means O3 over H beta is going to be higher because you have a matter bounded sector or H2 region. Another thing is that matter bounded nebula. So if I cut here, or even if I cut here, then I miss completely the N2 emission, I miss the S2 emission, the O1 emission, etc. And so that is going to change also the diagnostic power of these lines. If you want to distinguish between star formation and AGN, this is going to change completely. And as a result, low ionization lines like O1, N2, etc., they have been claimed to identify potential leakers. And that's because of that, basically, because you're clipping all the ionization front here. The sign that you have low ionization lines, weak low ionization lines, or that you don't even see them, might be a sign that you have a matter-bounded regions, and that might be a sign that you have escaping photons. If you have holes, though, that's not the case. So it's just a way to potentially select them, but it doesn't work all the time. But this is just to illustrate why considering matter-bounded regions is important. And this is another illustration of it. This is a very specific result, but I think it's very illustrative. So once upon a time, there was a problem with the electron temperature measured from the O3 lines in 15018, of course, and that high electron temperature remained a debate for many years. And so it was thought that the photoionization by hot stars was not enough. And so some people invoked different heating mechanisms like stellar winds, supernovae, shocks, maybe, etc. So the electron temperature is constrained by these lines here. But the key point is that it depends on the local density. And the local density in the previous works was derived from S2. But like I said before, the S2 density is the density at the ionization front, and it's not representative of the density of the entire nebula, because you might have a density profile, and the density is going to be higher at the ionization front, where you might have a shell here. And so in a pioneering work, what Pequigno in 2008 did is a combination of models with radiation-bounded shells embedded in a matter-bounded medium. So you have like radiation-bounded shells here, matter-bounded medium here, with a veil even extremely thin. And the effect of that is that it produces a lower mean density, and as a result, a higher electron temperature, and everything worked, and it was fully explained by photoionization, and you didn't need to invoke all these heating mechanisms, let alone population 3 stars. And as a result of this paper, Pequigno introduced the topological models, which are combination of 1D models. And at the end of the presentation, I will explain what we can do. We can do that in a systematic way with statistics. It can be very powerful. Now, you might also want to account for time evolution. Instead of looking at a given H2 region and PDR at a given time, you might account for the fact that it evolves with time. So this is not just a tweak to 1D models, it's 1D models coupled with other codes that are time dependent, but still it's using 1D models. And a good illustration of it is the paper by Eric Pellegrini, which did that code warp field EMP, which couples the stellar code warp field with the cloudy H2 region PDR code and the Polaris code, which does the line and continuum radiative transfer. And what they were able to do is make predictions for the time-dependent emission arising from the issue region and the PDR. You have here the different phases of the issue region. And so on the BPT diagram, depending on the phase in which you are, you're going to have a different location in this plot. So I encourage you to read that paper if you want more details, but this is one way to use 1D models and account for time evolution and make the best of 1D models and remove some assumptions. Okay, so now I don't know how much time I have, but maybe it's a good time before I reach more complicated models and configurations to take a break, a good breath, wake up maybe, and maybe some questions.
Okay, so do you have some questions? Ah, yes.
I'll go to the slides once. The 2 slides up when we're talking about once upon a time slide.
Yeah.
So when we're talking about density that is determined by S2 ions, which is saying is not representative of an ionized nebula. So it was in past, right? Now we do.
Now we do what, sorry?
And it is a representative ionized nebula. It represents the outskirts of the nebula.
Correct.
Right?
Yes.
Okay.
Yeah.
And okay, I think second will be clear with this.
No, so that's correct. So you might, so it's difficult to get density diagnostics. You can have different line ratios you can use different kind of models to use the density. What he chose was to use a combination of different models, but the result was that the mean density corresponding to the combination of models at different depth was lower because some models were radiation matter bounded. Yeah, but it's just an assumption. I mean, you can have different ways of dealing with it.
That next slide didn't say that it's like once upon a time is not, it's done.
Yeah, sorry, yeah.
I was waiting for it.
Yeah, it's true. No, the once upon a time refers to the long-standing problem, and the problem is solved at least through this configuration, which is which seems to work, and there's nothing wrong with this configuration, in fact. So, yeah.
So, are there more questions? What about?
Thank you for the talk, Christopher. When we talk about diagnostics for different, let's say for temperature or the density, would you suggest that we use different diagnostics and then find an average parameter, or would you say that there are certain diagnostics which are better than the other? Let's say if you're talking about optical in some sense.
So for instance, like the density diagnostics.
Yeah. So is there a preferred or more reliable diagnostic than other?
I guess that's the limitations of the empirical diagnostics, because they will be useful to measure some kind of parameter, density or temperature, but under certain hypotheses, and you have to know which hypotheses they are. So for instance, for the density, yes, it traces all these line ratios trace the density, but since the lines don't come from the same regions, then you don't trace the same part of the nebula, and because of the density structure, it's not you're not going to get the same answer. So if you do an average of all your values, I don't think it's very meaningful in a way.
Yeah,
so ideally, you would like to use maybe a more complicated model that will account for the density structure and that will be able to reproduce all the line ratios with a varying density then. And it's complicated.
right.
I know it's complicated. And it depends on the tracers you have available. So maybe you don't have all these line ratios to work with and you're going to have a single density anyway. So you have to work with what you have. But I think it's always complicated to derive some kind of average parameter and interpret it as some kind of average parameter, not knowing exactly if it is an average parameter. So I think the best we can do in these cases is just acknowledge the assumptions, the hypothesis,
Right.
and take them as they are and try to
Because, because when it comes to, like, let's say IFU spectrographs, each spectrum is different from each other. And then when we see certain lines in one spectrum, it might just not be there in another spec. So like
Sure.
certain line ratios. So yeah.
Yeah.
So how do you?
Yeah.
I see. Thank you.
It's complicated.
Okay, so I suggest that we continue. You have 50 minutes left, including
Okay, I
questions.
think it's more than enough.
Yeah, okay.
All right. So, so I talked about modeling full galaxies with 1D models. I talked about how it can be limiting because we have some regions that are that have complex geometries. And so now I will describe some mixing issues and why things are even more complicated than that, and why we it's kind of, maybe Jean would say hopeless, but we try to do our best to do to try to account for all the tracers. So there is evidence of mixing in galaxies, and why is it important to acknowledge that? Is because eventually, if we don't focus on a single PDR, a single H2 region, or a single molecular cloud, what we would like to do is try to build a comprehensive model that is able to explain everything if possible. So explain the multi-phase signatures, and a model that will be able to account for the complex ISM structure, the complex geometry of the sources versus the gas and versus the dust. And often, I showed that before, but unresolved spectroscopy, especially unresolved spectroscopy, is just inevitable. For instance, in very high redshift galaxies, it is going to be mostly spatially unresolved in the far infrared at redshift 0, etc. So we have to deal with it. We have to acknowledge that and try to make the best of it. Galaxies in general will include a collection of H2 regions, if it's a star-forming galaxies, H2 regions that will follow some luminosity function. That's something that we have to keep in mind. Some H2 regions will leak ionizing photons because they're going to have holes or because they're going to have some matter-bonded shells, etc. There might be supercellular clusters as well. All of that is going to result in some mixing of some model parameters that you might use, like the ionizing photons, number of ionizing photons, or the ionization parameter. A galaxy will also include a distribution of gas densities following some kind of PDF. And that PDF, as we'll show in the next slide, is related to different physical mechanisms. And that will include some density and pressure mixing. That might or not be a problem depending on the lines you use, because they have the transitions have critical densities. And if you are in the low or high density regime, you might not care actually about the exact density PDF. So that's something that we can discuss. A star-forming galaxies, a galaxy and a star-forming galaxy in general will have a collection of molecular clouds. Some molecular clouds are going to be associated with star formation, some not. And a galaxy will include Wolf-Rayet stars, high mass X-ray binaries, and if it's there might be an AGN in there as well. So I'm going to illustrate some of these things now. So this is from simulations. This is the density PDF of the simulation. So I think the density peaks around 1 or slightly below 1 per cubic centimeters, if I'm not mistaken. And you have 3 regimes. First one is associated to turbulence, then self-gravitation, and a third one that is rotational support. So this is something that you might want to take into account if you want to model a full galaxy. It's not a single density, it's a wide range of densities. Now, again, depending on the tracer you use, you might not care because if you use optical lines, you're in the low density regime, and so you can just consider that the line ratios doesn't depend too much on the densities or whatever. You have H2 region. So this is the H2 region luminosity function for several galaxies in the Fangs-Muse sample. So you have an example for one galaxy here with different regions. And I don't remember which one it corresponds to, but from that you can derive some kind of luminosity function. So you have a lot of low luminosity H2 regions and a few luminous H2 regions, but that are very important. And that's something you probably also want to take into account eventually in the models. Right. Here, I'm going back to this to the hypothesis of the effective H2 region. I mentioned that before. It's a common assumption to assume that all the ionizing sources are in the same spot, possibly even an AGN in there, and you have a shell of gas around it, spherical shell. And the question is it really the same as considering a collection of individual H2 regions or not? And so this is a simple test I did. So don't read too much into this because it really depends a lot on how the models are designed. But this is O3 over H beta, O1 over H alpha. So it's one version of the BPT diagram. And here I fix all the parameters, but U and H, so the SED shape, the stellar SED shape. So basically all the points here have different U's and different H's. The red points correspond to this hypothesis of the effective H2 region, and the blue points correspond to the collection of H2 regions. And you can see that in most cases, actually, they are here. It works very well for. So here, I don't have any X-ray sources. I don't have PDR lines. So it's dominated by absorption of UV photons by the gas. So both geometries are basically the same. And then you start to see some changes here. It happens at very high U values. And this corresponds to the thinnest nebula and also to a regime where the dust absorption might become important. We talked about the dust earlier, I don't remember when it was exactly, but I think it was yesterday. So the dust is going to have an impact on the absorption of the photons. You might be in a regime at high ionization parameter where the dust is going to start competing with the gas to absorb the UV photons, and you might be in some kind of dust-bounded H2 region where already most of the UV photons are going to be absorbed by the dust. I haven't checked here, but it's one of the effects that might play a role for this kind of regime here. But this is not too bad. So it works pretty well. Optical lines, UV photons, yeah, it works. And I think that's why basically this assumption was made in the past. This is not a big deal. Things start to get more complicated if you include X-rays, for instance, because X-rays don't follow the same rules as UV photons for the absorption. And so yeah, I didn't explain actually here, but for the same U and H, the line ratios change. Huh? So you might think I'm going to try to recover the red points could coincide with the blue points if I change the U, etc. And in fact, it's not that easy. It's not simple. It's an effect of geometry and not just the input parameters here. So this is just to show that including X-rays kind of changes everything. Here it's for a given X-ray luminosity, and it can get worse depending on the X-ray luminosity. And this is another test, this time with PDR tracers. You have O1 over C2, so we're in the neutral atomic gas, and here O3 over C2, and here the two configurations are completely separated. And the effective region model here would need to have a much, much lower density in order to match better the collection of models. So like I said, don't read too much into it, make your own tests. It depends on the definition of the U parameter, the ionization parameter. For instance, in cloudy, it is the ionization parameter at the edge, at the illuminated edge of the nebula, but a more meaningful parameter would be the volume average ionization parameter. And some of these things, maybe not here, but in the previous slide, are going to start to change. So this is just to illustrate the fact that this kind of hypothesis works, but under some conditions, not always. Then I did mention that I would explain the coincident and non-coincident mixing. So I said that with single 1D models, you assume that all the sources are co-spatial, so all the stars, all the stellar clusters, possibly an AGN as well. So this is this kind of geometry. It's called coincident mixing. You might have a plane parallel slab, or you might have a spherical geometry closed that will include reflection, etc. But you might have also non-coincident mixing. So here you have two 1D models, basically, one corresponding to the AGN and one corresponding to, well, mostly the OB stars. And again, you might have the plane parallel or the closed geometries. So these are two different geometries, if you care about AGNs, that you might want to try to test, because it's going to lead to slightly different results, slightly different diagnostics. Oh, and you might wonder actually, how do I decide which one is the right one? The answer is that it's not easy. You might try to see which one fits the best data, but that's no proof of whatever, except the fact that probably both will match the data pretty well. And so I think there are some assumptions that need to be made based on the exact object you're trying to model. And if you have an unresolved object, it gets very complicated. You probably cannot distinguish. So maybe the best you can do is do both and take that as some kind of systematic uncertainty based on the model assumptions. Okay, so I talked about mixings, the density, the H2 region luminosity function. There are other evidence of inhomogeneities in galaxies, of course. So one galaxy is not represented by a single parameter for any of the parameters that I showed, including the metallicity. And that should be kept in mind when we model a spatially unresolved galaxy. And here is a sentence from Culiel review, where she says the global metallicity of a high redshift galaxy may not be the true mean metallicity of this galaxy, but may be weighted towards some specific H2 regions, bright H2 regions, that may have a certain set of properties. And so that's really something that we should keep in mind. These are some IFU observations. This is the gamma SAMI survey, and you have the variation of metallicity. This is the dispersion as a function of the radius here. So you have some kind of gradient, but the dispersion here is really, if I'm not mistaken, so it's pretty significant. So you have variations of metallicity in your galaxies, and so it's not uniform. Maybe you can try to account for it, or at least acknowledge that it is not uniform. Now there are other issues that are revealed through IFU, IFS observations. This is an interesting paper showing that the stellar mass is underestimated by factors of a few if you consider the integrated SED, so the integral of the integral field spectroscopy, as compared to the sum of the mass you get for all the pixels. So this is for the photometry, it's not for the spectroscopy, but it is a very interesting result. So here you have the ratio of the unresolved mass. So basically integrating the entire IFU field and getting the mass from that. So you integrate the light, you have a single measurement, you get the mass, that's that. And then here you have the sum of the mass measured pixel per pixel. So it's supposed to be a true or better representation, a better measurement of the actual mass. And so this ratio, as you see, it starts declining quite a lot for galaxies with a high specific star formation rate. These are for spectroscopic redshifts. There is the same plot in their paper for photometric redshifts, and this is much more populated. And so you can make a mistake by a factor of a few. And this is interesting for me, it was reminiscent of the work by Frédéric Galliano, actually, on the dust mass estimates versus spatial resolution in the LMC, where he showed that the dust mass estimate changes with the spatial resolution. It's kind of the same effect that we see here. This kind of systematic effect, though, so I said it was from the photometry, and there are a few similar studies for spectroscopic diagnostics, for instance, to measure the metallicity, the star formation rate, or the mass of ionized gas, or whatever. But I think it will happen soon as we have more and more IFU observations. And about IFU observations, one thing I wanted to mention was that, so pixel per pixel, it means you get the mass for a given pixel, sure, but that doesn't mean that you're free from mixing, that there is a single component in your pixel. Because even for a single pixel in an IFU observation, you will have some kind of mixing due simply to the column of gas that you're probing along the line of sight. That's true for all the SAMI, MUSE observations. And so you might have some kind of complicated case. So imagine here you have an IFU observation. So I have 3 pixels here. So I remind you that each pixel is a spectrum in IFU observations. So that might be what you observe. You have some stars and you have some clouds, some emitting components. But in reality, what happens is really that. So you have a stellar cluster and you have some clouds that are illuminated by that stellar cluster. And then along the line of sight, further away, but still in the same object, you have other stellar clusters, other stars that illuminate their own cloud here. But what you see is not that, especially except if you have spectral resolution that allows you to separate in velocity the components, but it's difficult, and especially in the optical, you cannot get extremely high spectral resolution. So what you get is usually just that. And so you have several ionizing sources, several clouds, and you don't know which one ionizes which one, etc. So it's complicated. And on top of that, you have some clouds that are in some pixel, and so the ionizing sources are in another pixel. So you cannot just take one pixel and say, I'm going to make one cloudy model out of that. And because then what is the ionizing source for this one? And what is the ionizing source for this one? And for this one and this one, it should be the same ionizing source, but you don't give that prior knowledge in the model. So, you know, these are just complicated configurations. We try to make the best of it. But again, this is something to keep in mind. I'm not saying we have the magical recipe to solve that, but this is just something to keep in mind. And that's something actually that led us to consider incomplete models for IFU observations, where, so you can think of that as a line of sight, so in that direction here. And you have like a full model would be this. So this is the H2 region, this is the PDR in gray. So you have your full model. This is a spherical cloudy model. Okay, no problem here. But you might have a model which is matter bounded. I explained what it was already, and that can be 1 pixel here. But 1 pixel can actually be a naked H2 region with the cloud, the PDR, lying in another pixel. So your pixel might correspond to that. Yes, it can happen. It is physical if the other components are in other pixels. You might have even more complex geometries where you have several regions along the line of sight. So again, in that direction, some of them might be full, some of them might not be full. You might have lines of sight that intersect just a PDR and not the H2 region. So then you will have only PDR tracers. And so again, how do you model that with a model like Cloudy, which does H2 regions and PDRs? It's complicated. So there are several ways you can do that. In that paper, we explain that we can kind of clip the H2 region and the PDR and try to disentangle them and try to make for each line of sight a mix of H2 region and PDR. So you might be just 100% PDR, 100% H2 region, and so on. That's just one way of doing things. Okay, so I showed that there is evidence of mixing and smearing issues. So smearing, that's what we say for the IFU observations. Now, how can we try to improve that, or what kind of configuration can we use to make sense of it? So we can use more than 1D models, 2 3D models, and we can also use n times 1D models, so a combination of 1D models. So I'm going to walk you through that. So these are the different options. So combination of 1D models, pseudo 3D models. This is the like Cloudy 3D, M-Cube. I think I mentioned it right after. Yeah, I think so. But I will remind you what this is. Then you also have combination of independent 1D models that represent individual galaxy components. You possibly have the possibility to use the full 3D radiative transfer models, full 3D photoionization models. I will also explain in which cases you could or not. And you have the possibility of using simulations compared to your observations. I'm going to focus on lines and so gas spectroscopy. So I'm not going to talk about panchromatic ACD models. There are several review papers I encourage you to read, but here I'm going to focus really on the nebular emissions. So these review papers, unfortunately, don't tackle that. Here I'm going from the most simple to the most complicated, but actually I'm going to present them in the other way because I have little to say about that and more about that. So I'm going to start with the simulations. Simulations are great for many reasons. They include dynamical effects. They include a realistic and consistent ISM structure, like the density PDF I showed you. They include a realistic distribution of sources. It's physically motivated, blah, blah, blah. The chemistry, though, is numerically expensive, and actually most simulations do not include any form of non-equilibrium metal chemistry. And another thing is the resolution of the simulation is important, and simulations will tend to rely on subgrid models to account for the physics on sub-parsec scales, for instance, like resolving the ionization front. The simulations, what you can do is post-process them, so you can feed these simulations to photoionization codes or chemical networks in order to measure the metal ionization states and the emission, and that after the simulation has been run. And here I give you some papers of Michaela Hirschman, where she processes with cloudy and mappings simulations. Some simulations include a chemical network that is very complete, and they solve the chemical network within the 3D simulation. So here's an example with the combination of the thermochemical network PRISM with the on-the-fly radiation hydrodynamics code Ramses RTZ. This is a work by Harley Katz. And this is great because you can do full 3D cosmological simulations or isolated individual galaxy simulations. For instance, this is the N2 column density and plus column density for an SMC-like galaxy, like the Small Magellanic Cloud. So this is extremely powerful. You have plenty of physical processes in there. You can make maps of various column densities, heating rates, cooling rates. You can make synthetical observations that you can then compare to your actual observations. However, they are very expensive to make, so it's difficult to compare to a single galaxy, of course, and you don't make a simulation just for a single galaxy. It's, you can, but it's difficult. So the exploration of large regions of the parameter space remain difficult with simulations. Ideally, we would like probably to have thousands, hundreds of thousands of simulations with varied parameters, a bit like we do a model grid with Cloudy or Meudon PDR. And then we would like to compare that to the observations and make a simulation grid compared to the observations, etc. But still very, I mean, it's not yet possible, and that would be very long. That's also takes a lot of energy to do that, a lot of time. So in the meantime, we have to think of other solutions while keeping that in mind, because there's a lot of work that can be done between observations, model, and simulations to try to have all of them meet eventually halfway. And I will come back to that with what I mean exactly at the end of the talk. So such simulations are still very interesting, even though we cannot compare them to observations or specific observations, because they can be used to test what we call unmixing techniques, which is basically the biases in the spatial resolution. Because here we know what there is in the simulation it was fed. We know the density distribution, we know the metallicity distribution. And so we can try to design models that will reproduce these parameters. And we would like to reproduce the average parameter, for instance, the average metallicity in this simulation. We would like to find ways, model configurations that can reproduce this metallicity, and that then we can use that to apply to real observations. But we don't want to just reproduce the average parameter. We also want to reproduce the dispersion across the simulation here. That leads to many, many problems because it's not trivial at all. For instance, not all the pixels, not all the cells in the simulation here are going to lead to some emission, and the emitting species that you use yourself as constraints when you do models. So so the comparison is very difficult. Then you have also, of course, the biases due to instrumental uncertainties, etc. And what kind of model configuration would you use to try to reproduce the parameters in a simulations like that, knowing that if you wanted to do things very well, you would have the exact same thing as the simulation. But the point is that you can't. You would like to find 3D models, combination of models that get you the same average parameters and dispersion. So you might want to try other methods like full 3D radiative transfer. This is without photoionization, so it's line and dust transfer codes. Like RadMC3D, for instance, or SCIRT. So these codes are extremely powerful, but they are really adapted to objects with known geometries, but potentially very complex geometries. But you have to have some kind of knowledge of the geometry. In other words, the geometry is not a free parameter. It's not parameterized. So such 3D Monte Carlo or radiative transfer codes can handle very complex geometries. And so far, the application has been mostly limited to stellar populations and dust heating processes. But eventually, the future is really to do such codes with fully self-consistent treatment of gas and dust. So the dust and gas embedded in the photoionized nebula with arbitrary temperature, density, dust distributions. We're not there yet, but there are very promising avenues like the combination of SCIRT and Cloudy in this paper here. It's only the start, but full 3D MC RT codes have a bright future, I think. Now you might want to try also full 3D photoionization code. So in here, the photoionization is treated, the photochemistry potentially as well. This is very good. It's great, of course. It's expensive, computationally expensive. There are some examples of such codes here. And the main limitation, I would say, is that you need to know the distribution of matter and sources in your cube that you're going to have to put in there. And again, geometry is not a free parameter. That's what it means. And so that means it's particularly adapted to some specific objects, planetary nebulae, bipolar H2 regions, fractal H2 regions, etc. Anything you can think of, but this is not necessarily parameterizable. And so if I take all the 3D methods together, what are the pros and cons? 3D models are very good to do the radiative transfer in different projection in different directions. So it deals very well with the projection effects. This is something that we cannot do really with 1D, just combination of 1D models. It's very useful because we can try different geometries. Maybe it's not adapted to a specific object, but we can put different geometries in there and see the effect it has on some output quantities that we might be interested in, like the mass of ionized gas, etc. And of course, they are still steady state models, so they still can't capture the complex and dynamic structure of the ISM. So to finish on the potential configurations you can use, I'm going to go back to 1D and consider combination of independent 1D models. And the principle has existed already for quite some time in the late 90s, and it has developed really in the early 2000s, and even more now as we have more ways to consider many components in a statistical way. The principle is that you can consider that the integrated spectrum of a galaxy is the linear sum of many emitting components, stars and ISM, that may or not share similar properties. For instance, they may share the same stellar age, the same SED, or not. You can try to mix that if you want. And so this is an illustration here. The point of these studies was to remove the age parameter. It was a single free parameter, the age, and they kind of they removed the age parameter by considering a continuous formation of stellar clusters. Basically, that means that they were able to have a flux average spectra along this evolutionary track. And so that accounts for the fact that the H2 regions evolve, and that across the history of a galaxy, you're going to have some kind of smooth properties of the H2 region that depends on this evolutionary track. And so it's not really it's a combination of 1D models if you want, but this is really a nice way to account for the mixing of age in a galaxy. And this is just an example showing an H2 region evolving. It's stupid. More generally, what you can do by combining independent 1D models is just considering many components that contribute to one galaxy. And so that led to the idea of the locally optimally emitting cloud, which assumes that the cumulative observed emission from a full galaxy is the result of selection effects. And these selection effects, they stem from the fact that some lines emit optimally in certain conditions, certain physical conditions, depending on the density. So depending on the critical density, so the density of the medium, etc., etc. So you can think of your galaxy as hundreds, thousands of components. Each will contribute to some emission, and you would like to know which combination corresponds to the integrated spectrum of your galaxy. The advantage of a method is that it's fully parameterized. And here is the equation basically that just explains it. You have the luminosity of a line, which is just the integral of the luminosity that depends on all the parameters with some kind of integration weight. So it's a weight that you give to each component. And the goal is that you can infer that weight. So for instance, you will assume that the ionization parameter depends, is described by a power law in your galaxy. So you have different components and the ionization parameter will follow a power law because most things are power laws in the ISM, or the density as well. If it's not clear, I will show in the next slide what I mean exactly by that. So stick with me. And so that leads to the general idea of model architecture, which is, I go back to what I said before with the topological models. Topological models will be linear combination of completely independent 1D models. The 1D models don't talk to each other, but a bunch of 1D models. And I make the distinction between topology and geometry. The difference is that the exact way in which the components are distributed, spatially or not, we don't care really. What we care is what kind of mix of components exists. And the reason why we don't care is because the 1D components, they are independent, they don't talk to each other. So we don't care if one component is next to the other one or whatever. So that's why we talk about topology. Okay, so let me explain a little bit what I mean here. We can see. So imagine you have a spiral galaxy here. So you have different stellar clusters. So here there is only one star, but in fact, each cluster corresponds to a stellar population. So keep in mind that for each bubble here, you would have a stellar population. So you might think of your galaxy, when C1s means one cluster, one sector. Basically, it's just to say that you might think of your galaxy as the sum of a bunch of components. So basically it's replacing the effective H2 region hypothesis with a sum of a collection of H2 regions, potentially H2 regions that have PDRs also themselves, okay? So that's already a good test to do. Now we can do something more complicated and we can have two components, two different types of H2 regions if you want. So I have the one from before, and then I introduce some kind of new component, maybe a different ionization parameter. And I will say that my galaxy is a mix of this component, n times, if you want, n H2 regions, and another number of H2 regions with the different properties. And so I can try to parameterize that and find the best mix, the most likely mix. It's still not very realistic, even though it's an improvement, because it means we have two components and each component has a single U, right? And so it's as non-realistic as assuming that there's a single U, a single ionization parameter, or a single density for the entire galaxy. So it's a bit better because we introduce some kind of mixing, but can still do better maybe. And that's where we can introduce power law distributions. And I go back to the LOC, locally optimally emitting cloud hypothesis. And here you have different sizes for the spheres you can see. So they correspond to different U values, but you can see there is a continuous range of U values. And this continuous distribution is described by a power law distribution. So you have a lower bound, upper bound for the ionization parameter and the slope. And that will describe the U in this distribution, and the sum of all these distributions are going to give me the total spectrum of my galaxy. We can do more complicated and we can change the age as well. So the size of the star inside, and I remind you that each of them is a stellar population, it's not a single star. The size of the star is going to be correlated here with the age of the cluster, and that can follow some kind of power law distribution. Here it looks a bit smooth because it's a smooth power law to avoid sharp breaks at the upper and lower bound. Okay, we can do even more complicated. We can try to introduce the density also and say the density will change as well. And so here it's the opacity that will correlate with the density. And so you see that there is a distribution of densities following its own power law. And here it's a good occasion to say that everything is mixed here. So it's not that you have, or how to say, you can have a young age and low density, you can have old age and high density. Basically, the sum of it all follows the various distributions that I considered already. So this is all consistent. And I remind you also that they don't speak to each other, single individual 1D models. You can change the metallicity, so that gets a little bit too complicated here, but this is one way to account for the metallicity variations within a galaxy. If you have enough constraints, that can be something you're interested in. And so yeah, so that's one way to combine 1D models. In some cases, if you care about the escape of ionizing photons, or if you care about BPT diagrams with matter-bounded regions, you might want to have the physical depth of the cloud as a free parameter as well. And so I'm not going to show that for a full galaxy, but more for an H2 region because it's simpler. But the combination of 1D models can also be adapted to the case of an H2 region. And this is what I'm illustrating here. Right. So if you imagine you have your galaxy like that, you have a star forming region, you have a PDR in orange, you have molecular gas in the dark red, you have the 1D model with the stars and possibly a compact object. So that's already presented. So here is a radiation bounded model. And so, for instance, for that component of the galaxy, well, that might be enough if I use a spherical geometry, but it is not matter bounded. So now I would like to add the physical depth as a parameter. So for instance, there is another part of the galaxy where I don't have all the molecular emission I should, because this is clipped here. And so I can do a model like that, but just for that component. And why not? Then I can have a region that has only the PDR, but no molecular emission. So I have only these tracers here. And so that will correspond to this kind of model. And so on and so on. So here I have maybe a pixel in an IFU that corresponds just to H2 region. That corresponds to that model where we just see the H2 region. So 1D model spherically, spherical geometry. I can have matter-bounded H2 regions. So here some ionizing photons are going to be able to escape. And so at the end of the day, we can do many things with that, but basically it's always going to be a linear combination of these different components I just showed you. It can describe the entire galaxy, it can describe a given star forming region that has different sectors, different components, some that are leaking or not. If it's a single star forming region, you can represent it like that. I like to say this is the 2D representation of a 3D object modeled with a 1D code. And so you have 3 components in here. I guess it corresponds to these 3 here, I don't remember, but some components are thinner, the ionizing photons can escape, here the ionizing photons cannot escape. Anyway, my region is described as a combination of different 1D models. Again, they don't speak to each other, which is an important assumption. And so that's some kind of modeling approach we've been using in our group for several years. And I'm just showing, I'm not going to walk you through all of that, but these are just different configurations, depending if we want to use the diffuse ionized gas or not. The overall idea is that here we combine 1D models, one way or another. Here we have the diffuse ionized gas, here we account for matter-bounded gas, here we have different sectors, some of them are matter-bounded, there is an X-ray source. Here we have, that's what I showed you before, it's the spatially resolved observations where we have a fraction of, given fraction of PDRs or just naked H2 regions, but this is still a linear combination of 1D models. Here we quantified the PDR covering factor. So anyway, I just want to illustrate the fact that there are many potential applications to such configurations. And very quickly, these are some various results that were obtained with the combination of 1D models. I already showed that one, which was really the pioneering work, but then we applied that technique to star-forming dwarf galaxies to match many lines from the PDR and the H region at the same time, which is not easy, except if you do a combination of 1D models. Things related to PDRs and CO dark gas, and things related to the escape of ionizing photons. So I don't have time to explain all these results because this talk is mostly about the methods, but anyway, just to show that it's very versatile. And here I'm just illustrating some ongoing works on that topic. So this is very, very preliminary, but this is just to show what kind of biases you can have if you have a single 1D model for a galaxy, or if you have an LOC model, so basically a statistical distribution of clouds, like I just showed you in the previous slides. This is for the metallicity, this is for the density, for the ionization parameter and age. And so again, this is very, very preliminary, but you see that for the ionization parameter and the density, it works pretty well actually. So the average, or I should say the single value you get in a single 1D model is actually very, very close to the average value from the statistical distribution. So it works pretty well. For the density, there are some weird things happening here. For the age, it doesn't work at all. And then both are probably related here. So this is something we're investigating right now, but this is an interesting way to see potential biases that we may have if we consider a single 1D model versus a collection of different components. This is in progress, really. Another thing in progress is here you have some IFU observations, and there is the metallicity dispersion I showed you before. And we tried to, as a proof of concept, to say, okay, 1 pixel is a distribution of some parameters, here metallicity. So here, this is a distribution of metallicity within each pixel. So each line here corresponds to 1 pixel, and this is the entire distribution. And the question was, if I take all of that, I sum all the lines, all the pixels together, and I have a single spectrum, can I recover that distribution here? And it works surprisingly well, actually. Now, of course, this is just a very, very preliminary result. But the idea is that if you have enough tracers, you can start thinking of maybe recovering internal variations within your source, even though you don't spatially resolve it. And the idea is that your diagnostics are powerful enough. It includes lines with different properties that might make it possible. And if it doesn't make it possible, then the idea is to know what kind of tracers you need in order to make it. And such techniques have been used for high redshift galaxies. So multi-sector approaches, as we say. This is an H2 region, and you have PDRs, but the PDRs, as you see, they don't cover the entire H2 region. So it's incomplete PDRs, and some ionizing photons are going to escape from it. And that was done for the high redshift universe for some galaxies for which this is O3 versus C2. The O3 over C2 ratio is huge, really. There's much less C2 than what you expect. And it's difficult to explain with photoionization models. But if you have this kind of models where you have incomplete PDRs, then you have less C2 just because you have less PDRs. And so that explains naturally why you have some the O3 over C2 ratios like that in the high redshift universe. And this is another example of combination of 1D models. This was for JWST, to prepare for JWST with different dust distributions. This is just to show that this kind of approach with holes or with matter bonded regions, etc., can be applied even for the high redshift. Here it's for the epoch of reionization galaxies. So these combinations of 1D models, they appear quite powerful, but actually they have a bunch of caveats, and it's very important. They are still 1D models, so they're still static, steady 1D models. Steady state 1D models. The components don't talk to each other. It's a huge assumption. The projection effects are difficult to handle. We're not doing 3D here. We're not doing radiative transfer in the lines or in the dust. And so it's well adapted to optically thin tracers and dust poor ISM. But if you start to deviate from that, the orientation might start to matter. There are still parameterized models. Like I said before, it means we explore a wide parameter range, which may be not even physically realistic. So that can be solved if you have some priors in a statistical framework, but by default, the parameter space can be really big. And I think that, so I have a few minutes left, 5 minutes, so I will have to go quickly on that. Combinations of 1D models, as you see, there are potentially many models to make sense of. Actually, there are not so many free parameters because all these models are linked through some kind of statistical distribution parameter like the power law, for instance. So it's not that many free parameters. In any case, if you have many components, if you start to have many components, many parameters, then you do have quite a few free parameters. And the question is, how do you find the best, the PDF of your parameters? So you can use probabilistic methods that work very well. I'll go very quickly. There are several tools that exist to go through grids of photoionization, actually any kind of grid, to calculate the Bayesian likelihoods using brute force or step methods, samplers. The random walkers are interesting, but the ISM model grids, like I said, are multimodal, and it's worth, if you start combining models, you're going to have different solutions. So it means a sampler can get stuck in local likelihood maxima. There is a stochasticity OC, meaning that you get a different solution if you start from different points, and it's difficult to probe the entire space. Yeah, I'm not sure. I guess I will skip. Maybe I will just talk to you about, let's see. Let's see if I can show you this one. I think it's a good illustration. So these are two samplers, and this is just to show that depending on the sampler that you use, it might be more powerful really for the question you're trying to ask or for the type of grid you're trying to explore. So this is a type of Hamiltonian sampler called NUTS, no U-term sampler. And here I have two models. I mean, a model with two components, same U and different Z. Here it's nearest neighbor interpolation. Here it is linear interpolation. And you have 4 different colors corresponding to 4 different chains. And you can see that with the nearest neighbor, the sampler kind of switches from one solution to the other, but it's a 2-component model. Huh? So it's a 2-component that reproduces my galaxy. So I need these 2 solutions. With the linear interpolation, some chains get stuck in a local likelihood maxima, and that's not good because it's going to think that my galaxy is just that, but my galaxy is not just that. I don't remember the parameters here, but I think it's like 30% that and 70% that, and I linearly combine. But some chains get stuck, and that's too bad. But you can use other types of samplers. So one of them is the one we use is sequential Monte Carlo. So some kind of particle filtering techniques. And instead of having a few chains, like 4 or 5 chains, etc., we're going to have thousands and thousands of particles. And each particle is going to have its own Metropolis Hastings chain. If you know Bayesian statistics, maybe you know what I mean. So each point here is going to be updated if you want. So we start from the full prior space, and then the samples get redistributed. They evolve through their own chain, with the posterior being calculated. There is what's called the temperature to know when we converge to the posterior. And at the end of the day, you see that the fact that it is a multimodal solution works just fine for this kind of sampling techniques. Even for the linear interpolation, you see that slowly we converge to these 2 points, which are our 2 components in this galaxy. So this is just an illustration. And to finish, I just want to say that usually when you have an integrated galaxy spectrum, you don't know what to use as a geometry. And so usually you will assume a very simple geometry because you have few tracers. And that's fair, I think. And as you have additional tracers, then you might want to try to increase the complexity of your model. But I think it's interesting to still consider more complex geometries, even with few tracers, because these more complex geometries are more realistic. And so I asked the question, is it better to use knowingly an unrealistic geometry and then possibly infer inaccurate results that may be very precise? Or is it better to use a realistic geometry that is difficult to constrain and have an accurate but very imprecise result? And my 2 cents is that I think we have to accept the imprecision of the result and rely on techniques like hierarchical Bayesian methods in order to gain as much precision as possible. But my message is it's interesting to still explore complex geometries and see what kind of uncertainty we have on the parameters, even if we have few tracers. And I think the rest is too complicated and I don't have time, but if you do have questions on how do we make decisions based on the various models we have, based on the marginal likelihood and this kind of things, then I would be happy to answer it. If you can check that online also if you want, but I guess this deserves some kind of explanation. If you're interested, I can discuss it. And I think that's it. I'll stop here. Thanks.
So we have time for some questions. No questions.
So On your first part, you showed plenty of diagnostics of line ratios, but how many are unambiguous? Which fractions are completely unambiguous?
I guess it depends on the diagnostic diagram. That's a hard question to answer. As a matter of fact, I would say none is unambiguous. You have to have very specific tracers, and that's why I mentioned the coronal lines actually to trace AGN activity, because they are the least ambiguous tracers you can think of for the AGN activity. Now, if you're talking about other processes like shocks, for instance, and how to distinguish between shocks and AGNs, then I'm not sure. I don't know how to answer that. Yeah.
But maybe no single tracer is unambiguous, but maybe a combination of several can be.
But that's always the power of having different line ratios typically, or combinations of line ratios or sum of lines or whatever. Yeah, you gain in some breaking some degeneracies. Yes, sure. Yeah, but anyway, it's through model grids that you're going to understand really what's happening. So yeah, it's a tough question. Yeah.
Hi, great talk, thanks. I guess I also have a related question. In one data set I was working with, there is this problem that the N+, for example, N2 is, there's some photoionization flows involved, for example, and that kind of splits up the line sometimes. And there are also a lot of local effects that you see in the nearby regions. But I was wondering how you make a judgment call when it's a nearby galaxy, because then you can't observe these small changes in velocity, or maybe these kind of split lines. So how do you deal with ratio diagnostics in that case?
So your question is what exactly? Can you?
Just extending the ambiguous line ratio problem. Sometimes the line ratios are not easy to get, because sometimes the line is even split because of dynamical effects, like like photoevaporation flows or shocks, like you mentioned. So
okay, I see what you mean. Yeah. I don't know how I would deal with that, but I guess you can try different things. If you suspect there are outflows, then you can already probe some kind of contamination in your line due to the outflows and all different components in velocity, see what effect it has on the diagnostics. If you don't have any information a priori, anyway, it's hopeless, right? So the best you can do is probably to do some kind of best guess on physically motivated hypothesis about the range of the luminosity of your line that is contained in the outflow. Basically, that would be the pedestal emission of your lines, I guess, and yeah, see what kind of effect it has. But I don't think there's any easy answer to that. You know.
Maybe.
I have a bunch of questions in there and no answers. I just want you to know that.
I have a stupid question. No, it's really stupid. It seems to me like one of the most important aspects is the number of escaping photons, ionizing photons and dissociating photons that are escaping in or which are reprocessed, in fact, by the matter, right? In this model, this has solved a few discrepancies.
Right.
Yeah, right?
Yeah.
Do we have an idea with the observation of the full ICD of galaxies? I don't know. I have no idea. What is the percentage of how can I say that? Of what is the chances of the full distribution of galaxies that we have observed that the photons are escaping or not? That the ionizing photons are escaping?
It's a very wide topic. But first, actually, it gives me the opportunity to say that if you do have escaping photons, for instance, if imagine some of them are matter bounded, you have some escaping photons here, then they might actually be absorbed somewhere else. And the fact that the 1D models are independent is a problem in that regard. So I want to do that first.
Okay.
Then, I mean, so we know that so there are some samples like what's the name of the LZLCS that actually try to select some liquors based on some line ratios, and then they observe them in the far UV. They measure the continuum, the Lyman continuum. They did measure the escape fraction. So there is a range of escape fractions. Most galaxies have escape fractions well below 10%. Then there are a few exceptions to that rule. I don't know if they transform that into some kind of PDF, if that's your question, but most of them, it's a very low ionizing photon fraction escape. So with this kind of combinations, what we try to do actually is to figure out how the estimate of the escape fraction of ionizing photons change with the spatial scale. That was an interesting test to do. The idea being that if you consider a single H2 region, it might actually escape photons to a quite high level. It's possible because you have holes, etc. Sure. The galaxy escape fraction is expected to be quite low, except in some cases where you have galactic outflows or other things like that, yes. And so we just did that as an experiment for one galaxy, but the idea was to know whether the escape fraction was going down as you integrate more and more of the galaxy. And in fact, it does. So that was reassuring for this kind of model we're using. And basically that means that if you consider an entire galaxy, then you have more of the tracers like the PDR tracers or the low level ionization lines like N2, S2 typically, or O1. And so globally on average, that corresponds to a low escape fraction. And so it seems that there is not too strong biases for that. So I'm not sure I answered your question.
No, it's perfect. No, it's exactly what I wanted to know. Is what I really wanted to know is, can we do an energetic balance? And what you seem to say is that yes, because the escape fraction is quite low. So
right. Yeah, but it's not self-consistent here.
Okay, so maybe last short question, if you want to have a break.
There can be a dominant like physical processes. Is there any way to determine the optimal weights amongst the model?
I mean, that's the point of this kind of combinations actually. The AGN fraction typically can be a free parameter here. So you can assume that there is one AGN in your galaxy and make that a free parameter in that component. So that would be one way to do that. I'm not sure if that's what you mean, or do you, yeah.
Oh, I mean, not in terms of a model, but then in terms of physical processes occurring in the galaxies, right, which can attributes a lot to a line.
Yeah.
A certain line.
So you mean you would like to know if a specific line is excited by a specific,
exactly.
Yeah. That's true. Yeah. So if you have a combination like that and the models don't talk to each other, then you can technically, because then you can know what the lines, where it emits exactly in which component. And if it's the one with the AGN component, then you know how much of the line luminosity comes from the component with the AGN. And I think you can try to answer the question like that. But out of the blue like that, to associate one particular transition to a specific excitation mechanism, especially with combination of models, I'm not sure that's so easy. Yeah.
Okay, maybe that's a good subject for tomorrow's discussion. So thanks again, Vianney.
Sure.